Welcome back. This is video lecture 23.5, part 1. And I'm going to talk about section 5 in chapter 23, where we are going to apply Gauss's law for calculating an electric field, again to a situation where we have a charge distribution with a lot of symmetry. Planar symmetry, flat sheet that goes on in 2 dimensions. Okay? That's what we want to be able to calculate the field for. So here's what we have. We have an infinite in extent, non-conducting, so insulating, planar, flat sheet. Okay? And it has uniform surface charge density sigma all over it. So what you might imagine is like that kind of plastic cling wrap that you get at the grocery store that you pull and peels off a little cylinder and then you tear, and you could lay it out flat. Just imagine a very, very big in extent one of those sheets. 2-dimensional, flat, goes on and on and on one way, let's say length, and the other way, width, but has basically no minimal thickness. And it has a uniform charge per unit area, sigma, spread around all of it. Let's calculate the electric field for that. Now, the little schematic here on the right is trying to represent that sheet. It's that green, flat-looking blob that has little plus signs all over it. That's the sheet. And the plus sign is trying to represent the uniformly spread out charge with a charge per unit area sigma. You can see plus means we're going to assume it's positive charge. Now, because this is a very symmetric distribution, flat and goes on and on and on in 2 directions, that's a lot of symmetry. And just based on that, we can deduce some properties of the electric field. Okay? So the symmetry of the charge distribution dictates properties of the electric field. And here I'm going to tell you what those are. First, the electric field produced by this sheet must be perpendicular, and if it's a positively charged sheet, away from the sheet at any point, perpendicularly away. And it can't have any component that's like parallel to the surface. It's got to be perpendicular. Why can't it have any component parallel to the surface? Because if it did, if the electric field didn't point perpendicularly away from the sheet, but leaned a little bit, say to my right, then that would imply there's something special about looking rightward compared to looking leftward. But as far as the charge on this sheet is concerned, left and right look exactly the same in terms of what the charge is, how it's distributed. You see what I'm saying? The symmetry of the charge distribution dictates how the electric field behaves, because the charge is what creates the electric field. So the electric field has to point perpendicularly away from this sheet. And in terms of depending upon any kind of coordinate or position, the only thing that the magnitude of the field can depend on is the perpendicular distance, r, that you are from the sheet. Okay, right there, r. It can't depend upon any coordinate parallel to the sheet, but only the distance perpendicular from the sheet. And it's with that knowledge of how the electric field must behave that we will then pick a Gaussian surface that will enable us to solve for E. So we're going to choose a Gaussian surface that has, it's still going to be kind of a soup can shape, a cylindrical shape. Okay? It has sides, this Gaussian surface has sides that are either parallel or perpendicular to the sheet. Every bit of it has to be either parallel or perpendicular. So what we have over here on the right is a drawing showing the Gaussian surface. So what you should imagine is a cylinder. In this case, it's kind of on its side so that it can cut, kind of like a cookie cutter, right through the sheet. And it's got circular end caps on the right here. There's one of area A. And then it's symmetrically got a circular end cap on the other side of the sheet, also a distance r, and that end cap has area A. And then it's got a curved side. Okay? So really the Gaussian surface, the whole thing, is shaped like that. Whoops, guess you can't see the whole thing unless I do that. And we have just inserted it so that it slices through the sheet of charge symmetrically. In fact, right below is a side view. Let's look at that. Okay? The sheet is shown here in green with the little plus signs all over it going up and down indefinitely and into and out of the screen indefinitely. It's a two-dimensional sheet. And then there you can see the Gaussian cylinder in cross-section. It might look like a rectangle to you, but you're looking at a cylinder that's been turned on its side. Okay? And that's the Gaussian surface we're going to use. And our next task, once we've chosen the Gaussian surface, GS, is to derive a symbolic expression for the electric flux in terms of the electric field magnitude and the dimensions of the Gaussian surface. Remember, the end caps have area A, okay, whatever that might be. So what we have to do to figure out the expression for the electric flux, well, is we start with what that means, integrate the electric field over the closed Gaussian surface, electric flux. That means we got to be able to visualize where the electric field is piercing the Gaussian surface, because that's where you get your flux. Where is the piercing happening? And the side picture is trying to help you see that, hopefully, because you can see the electric field lines. Notice how they point perpendicularly away from the charge. See them here? Doot, 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 on and on and on like that. So where do we have electric field vectors piercing the surface, this Gaussian surface? That's the key question we're going to be able to visualize. Do you see where the piercing is happening of the Gaussian surface? Did you say the piercing is happening on the circular end caps? A little bit easier to see up here. There and back there. Or, as far as this side view would be concerned, the piercing is happening on that end cap on the right and that end cap on the left. In fact, you can see the E and an area vector for each of those end caps. But you see that the electric field is only skimming on the sides, like along here. On the curved side, here, or here. That's not piercing. So there's no flux through the curved side, only flux through the circular right and left caps. That makes sense? So you want to break this up into two parts. E dot dA over the curved side, whoops, plus, let's do better than that, plus E dot dA over the right cap, and E dot dA over the left cap. And we just argued that there is no piercing of electric field through the curved side, so that's 0. And so we only have to worry about the electric flux through the end caps. Let's do the right cap, and I'll explain what happens with the left. So let me try to draw the Gaussian surface. Here's part of the curved side, and there's the circular end cap on the right. And the electric field vectors are all pointing to the right. I'll draw one of them. Okay? And there's a little patch of area right there. So there'll be a dA for that, won't there? And so we're going to integrate over this right cap E dot dA. But look, the E and the dA are pointing in the same direction. So that's magnitude E, magnitude dA, cosine of 0 degrees. And the cosine of 0 degrees is 1. So now this is magnitude E times magnitude dA. I'm just going to use now the symbol E as for magnitude and dA for that magnitude. Now there's one more key step, and this is a vital one. Every point on this circular end cap is the same distance, r, from the sheet. The sheet's right over here to the left, right up and down. That distance is r. Every point on that circular end cap is the same distance, r, from the sheet. And we said that that's the only coordinate that the electric field could depend on. Therefore, I can know for sure that that electric field magnitude on that circular cap is uniform, constant. And that means, for the integral, I get to bring it out front. So add up all the little dAs on that right cap. And you just get the total area of it, right? And that's just called A in our picture. So that's the symbolic expression for the flux through the right cap of the Gaussian surface. Now, what do you think you get for the flux through the left cap? Let me draw that part. Circular end cap. Okay, which way does the electric field point over here? Now remember the sheet is now over on this side. Distance r. Well, the electric field points straight away from the sheet, and so would the dA, right? So do you see that it's the exact same situation as on the right cap? Exact same situation. So the integral over the left cap of E dot dA is going to give exactly the same expression, E times A. So what is our symbolic expression overall for the electric flux of this Gaussian surface? I have a factor of E times A from each end cap and nothing from the curved side. So 2 times E times A. And let's number that equation. That's important. Okay? The whole reason that the Gauss's law approach makes it possible for us to solve for E is when we have enough symmetry that we can pick a Gaussian surface. Either we get no flux at all through part of the surface, or we get this nice surface where the electric field is uniform and the E can be brought out front of the integral. If you can't pick a Gaussian surface where that's allowed, then Gauss's law isn't going to be that helpful. But we can do that in this case. So now we have that expression for the electric flux. Now we just need to know the total charge inside our Gaussian surface. So let's go back and look at the picture up here. Let me declutter the top picture. Okay, there's the Gaussian surface. So you got to be able to visualize now where inside that cylinder, and again, they only show kind of half of it shaded, but remember, it extends in an equal distance on the backside of this sheet. Where inside that Gaussian cylinder is their actual physical charge? Do you see where it is? It's right where the Gaussian cylinder, kind of like a cookie cutter, cuts through the sheet itself, which is right there. And that's shaped like a circle of area A. So how much charge is in that area that I just shaded red? That's what the Q enclosed is. Well, that's why we needed to talk about the charge per unit area of the sheet, sigma, which is uniform. So you just take the charge per unit area of the sheet times that area A. Okay, we'll call that equation 2. That was simple, wasn't it? Now we combine the symbolic expressions for the electric flux and the Q enclosed with Gauss's law and solve for E. Okay, so here we go. Phi electric equals Q enclosed over epsilon 0. And we substitute equation 1, the symbolic expression for the electric flux, in there. And equation 2, the symbolic expression for Q enclosed, in there. So we get 2EA, right? That's equation 1. See it? Equals. From equation 2, sure you can see it right there. For the Q enclosed, we write sigma A, and that's divided by epsilon 0. And one very important thing happens at this step. Divide out A. Remember, A was that cross-sectional area of the Gaussian cylinder that we chose, way up there. Now, we chose that Gaussian cylinder. Okay? So that A had to go out, had to cancel in solving for the electric field E of the sheet, because the electric field E of the sheet cannot depend on some choice that we might make about the shape of a Gaussian surface. So the fortunate thing is that that A canceled out, and so when we solve for E magnitude for this sheet, this is just the magnitude of the field, we get the charge per unit area of it over 2 epsilon 0. And so now, on the next slide, I summarize this result. Okay? So we've redrawn the sheet there, and the picture shows it as positively charged sheet. Sigma is positive. And now we know the formula for the magnitude of the field due to the infinite non-conducting sheet with uniform sigma. E magnitude equals sigma magnitude over 2 epsilon 0. And notice, it didn't depend upon this distance r, did it? That the cap is from the sheet itself. Doesn't depend on r. That means I could have chosen the Gaussian surface twice as long as this one, and I still would have gotten the same value for E. That means that the electric field produced by an infinite sheet is uniform. It's got the same magnitude everywhere. It doesn't get any weaker as you get farther away, because it's actually, according to our thinking here, infinite in extent. That's important. It's a uniform electric field. It depends only on sigma. I mean, epsilon 0 is just a universal constant. Okay? Now, what about the direction of the field? That's important. We got a formula for the magnitude. Well, if the sheet has positive charge, so sigma is positive, then the field points perpendicularly away from the sheet, like our drawing shows. Right? On the right side and the left side, the electric field vector E points perpendicularly away from the sheet. You could have a sheet that is negatively charged, so that the charge per unit area sigma is a negative number. The picture doesn't show that, but you could. Then the electric field would point perpendicularly toward the sheet. Just take each one of these E vectors and reverse their direction. Okay? Okay, that's what we want to remember for this section. Now let's just do a little applying of it, okay? All right, I want to apply it to a very important special case. It's going to be the topic of one whole chapter coming up soon. And here's what it is. I want to figure out the electric field created by two infinite in extent, going, front, back, left, right, conducting plates that are parallel to each other. Now, these plates are conducting. So they're both made of some kind of metal. And you're seeing them here with a side view. And so each plate goes on and on and on, up that way, down that way, up that way, down that way, and on and on and on into and out of the screen. And they're made of metal. And it just so happens in this picture that the left sheet was given some amount of net positive charge, and that's going to show up on its right surface. And the other sheet is given an equal amount of net negative charge, and that shows up on its left sheet. Why do they show up on those sides? Because opposite charges attract, and they want to get as close as they can. Okay? So one of these conducting sheets has been given a positive charge, smeared out over an area, so it's got a certain sigma, charge per unit area, and the other one has an equal amount of negative charge smeared out over it. So it has a sigma that's equal to the other conductor, but negative. I want us to figure out the electric field this creates. And the reason this is important is because this device is called a parallel plate capacitor. And capacitors are very important circuit elements when you study electric circuits. So it's very important to us that we know the electric field that this kind of configuration creates. Well, all I need to answer then my question as to what electric field is to use this result right up here. Because what I have is two infinite sheets of charge that are parallel to each other. Okay? All right, so I'm going to break up this region here in my picture. I'm going to break it up into three regions. To the left of both plates is region 1. In the middle region between both of them is region 2. And to the right of both plates is region 3. And I'm just going to treat these charge distributions as two infinite, planar, uniform distributions of charge. One positive, one negative. And use that result right up above. Now let's work first in region 2. Let's figure out the net electric field, magnitude and direction in region 2. So what I've got, I'm just going to draw the charges, is a positive planar charge distribution that goes up and down and in and out of the screen, and a negative planar charge distribution of equal amount, but negative, that goes up and down and in and out of the plane. And let's look in this middle region, and let's write down the formula for the electric field that each distribution causes. Look at the positive charge first. Okay? I want the magnitude and the direction of the electric field, say right there, at a point in the region in between, from just the positive sheet. Think about that a minute. Pause the video if you need to. Really think about it. What way does the electric field point at that place? And what's its magnitude for just the positive sheet of charge? Okay, did you draw an arrow something like that? That's the direction of the electric field at that place from the positive charge. So I'm going to label it E plus, right? Because it points perpendicularly away from the sheet. Now what about the contribution at that same place from the negative sheet? Think about that. Okay, did you draw an arrow also to the right and exactly the same length? We could label that one E minus. That's from the negative charge. Because for a negatively charged sheet, the field points towards it. But the two sheets have equal magnitude of sigma. And so the net electric field, right, magnitude of E net at any point in that interior region is 2 times the magnitude of either one of those fields, like that. And that is 2 times sigma over 2 epsilon 0, right? Because the field of one sheet is sigma over 2 epsilon 0. And I just double it. So what I get for the electric field magnitude in the middle region is sigma over epsilon 0 and directed to the right. So the actual physical electric field here is that. And it's the same everywhere in this middle region between them. Absolutely the same. Same magnitude, same direction. Okay, does that make sense? All right, now let's look at region 1. So now I'm asking about the net electric field at a point, say, over here, to the left of both of them. First, draw the electric field E plus from the positive sheet. Okay? Did you try it? Did you draw it that way? Right? Perpendicularly away from the positive sheet. Now, same location. What's the direction of E minus? Electric field from the negative sheet. Heads up. The presence of the positive sheet does not affect the contribution from the negative sheet. Ignore the positive sheet. I'm asking now about the negative sheet. Draw the E minus. Well, did you draw this? To the right, towards the negative sheet. negative, towards it. E minus. Now those two have the same magnitude. So what do you get when you add them? You get an E net of 0. There is no field outside the two conductors on the left side. So think about it for yourself a little bit, and you can convince yourself that there can't be any field on the right side either. So you have the very interesting phenomenon with two infinite planar sheets, one with plus sigma and one with an equal amount of negative sigma, that you get a nice uniform electric field in the region between them, and we have a formula for it, sigma over epsilon 0, pointing away from the positive sheet and towards the negative sheet. And on the outside region, on either side, you have no field at all. That is a very handy result. Okay, so the only thing I'll do here now is leave you with a class engagement exercise on Blackboard. Okay, practicing with electric field and what's called planar symmetry, these flat sheets. All right, the figure over here on the right shows 4 things. The cross-section of a large non-conducting sheet with a uniform surface charge density negative sigma 1. There it is. That's where it's located. It continues on up that way, on down that way, out of the screen and into the screen. You're looking at it as a cross-section. Negative sigma 1, so negative, uniform surface charge density. Also a point P, at which we're going to measure the electric field magnitude, E sub P, right there, which you can see, a little bit is cut off, sorry. There it is. That point P is a distance D from that first sheet. 3, an empty slot on each side of the sheet where we can place other sheets. There's an empty slot to the left, distance D, and an empty slot to the right, distance 2D from the first sheet. And then lastly, 2 large non-conducting sheets with uniform surface charge densities of plus 2 sigma 1 and plus sigma 1, here and here. Now they're just sitting down there right now. They're waiting for us to use them, and we can put one or both of them in those slots. So here's the first task. Move one and only one of the positively charged sheets to fill an empty slot such that the electric field at point P is equal to 0. You've got to decide which of those 2 positive sheets down there is to be picked and which slot is it to be put in such that the total electric field right there at point P is equal to 0. Okay? Which sheet and which slot should it be put in? And then, now you're going to move both positively charged sheets into those slots. But again, your goal is to end up with an E at point P equal to 0. Notice, by the way, you have to draw a picture of the 2 sheets and the arrangement in point P in part A. And then you have to draw a picture of the 3-sheet arrangement and point P in part B. Because now in part B, you have to use both of those positive sheets. And you got to decide where they go. Which sheet goes in the left slot? Which sheet goes in the right slot? Remember, the negative sheet is already where it is. But your goal, again, is to have a total electric field at point P equal to 0. Okay? That's your class engagement for this video lecture. Now, there'll be another video lecture coming, so that will be coming over the weekend. But that's all now for this video.